This lecture, video lecture 28.2, is going to be focused on one topic, one specific application of the physics of a moving charged particle in a magnetic field combined with a charged particle in an electric field. In other words, it's really a continuation of the previous section. And we're going to talk about a situation where the electric field and the magnetic field, those two fields that our charged particle is in, are crossed, which remember means perpendicular to each other. Okay? And this application turns out to be quite a famous phenomenon, discovered in the 1800s, and has been used as an experimental tool ever since. It's called the Hall effect, and that's what everybody calls it. But it's really just the physics of a charged particle moving in a magnetic field and also in an electric field. Now, we're going to do this specifically within the body of a conductor, a conducting material, like a metal of some kind, which, remember, the hallmark characteristic of a conductor is that it has internally a huge number, practically unlimited number, of free or mobile charges. And that in many simple metals, those free charges are merely electrons. So we're going to be focusing on a conductor with moving charges in a magnetic field and an electric field. Here's the experimental setup. We'll just assume, to have something specific in mind, that our conducting material is copper. Okay? Copper is one of those metals where the free charges inside are indeed simply electrons. And we're going to get ourselves a piece of this copper that has been particularly shaped to be kind of like a long, flat strip. And the closest thing I can think of to show you would be like a book, except not this big. All right? I think of the book as being thin this way, then it's got a certain width this way, and a length this way. And I'm assuming the length part of this copper strip is going this way, and the width is going this way, and the thickness is going this way. And we're going to hook up this copper strip, this conducting material, to a battery or a power supply so that there will be current, conventional current, assumed to be the motion of positive charges, this way, in and out. Okay? And so now what we're seeing here in the drawing on the left is a top view of this copper strip. So for my book, it's like I'm looking down on it from above, this way. Okay? All right, and so when we do that, it looks like what you see here. See the part in orange? That's the copper strip. And it goes on and on and on that way and that way. And it's got a certain dimension this way, which if you want, you might call the width. And it's got a certain thickness going into the screen, which you can't even see in this top view. Now we have set up, as I said, a conventional current I, flowing as we look down from above in this direction. Okay? Kind of top to bottom, although I'm looking down from above like on a horizontal surface. Okay, so there's conventional current flowing, quote unquote, downward in the plane of the screen. What that really means within the piece of copper is that conduction electrons, mobile electrons, are drifting, remember the drift speed, opposite to the direction of the conventional current. So here you see one example conducting electron and its drift velocity, VD arrow, opposite to the conventional current, because the conventional current is assumed to be the motion of positive charges. That just means that the actual conduction electrons have a drift velocity in the opposite direction to the current. Now we have also immersed this copper strip in a nice uniform magnetic field, perhaps because we put it near a magnet of some kind, either an electromagnet or a permanent magnet. And this picture assumes that this nice uniform magnetic field is directed down into the screen. And the way they represent that in the diagram is by drawing this series of equally spaced X's throughout this region, like so. I'll draw a few of them, and it goes on and on. And those X's are meant to represent the back end of an arrow, where the feathers would be, if that arrow was traveling away from you. And so it's that kind of a diagram that depicts this magnetic field. It's important to know the direction of it. It's perpendicular to this surface, this strip we're looking at from above, and it's going straight down into the screen. All right, so now we just want to kind of think through the physics of what's going on with these moving conduction electrons in the copper. Remember, they're drifting, these conduction electrons, with a drift velocity, quote unquote, upward in our top-down view. All right, so what we learned in chapter 28, section 1, is that if I have moving charges in a magnetic field, there can be a magnetic force, F sub B, on those charges. And the formula for calculating that, Q times V cross B, velocity cross magnetic field. Of course, the velocity we mean here would be the drift velocity of the conduction electrons. So I want us to figure out all that we can about this magnetic force on these conduction electrons. And let's just think of the example one that you see in the picture. First, let's figure out the magnitude of the magnetic force on a conduction electron. For that, you need to remember what we learned about vector products. If I want the magnitude of a vector product, in this case FB, it would be magnitude of Q, because technically the Q is negative, right? Magnitude of the drift velocity, VD magnitude, magnitude of the magnetic field, sine of the angle, what angle? Between the drift velocity and B. Do you see what that angle phi is in this case? Can you tell from the picture on the left? Well, in this top-down view, the drift velocity is going up, but the magnetic field is going in. That's exactly 90 degrees. So we're taking the sine of 90 degrees. Remember, the sine of 90 degrees is 1. So the simplified way all the books write this then is, now this is just the magnitude of FB, like that. And in fact, your book will write it like this, where everything's a magnitude. I'm a bit hesitant to do that because I want to emphasize that Q was negative, and so I need its magnitude. But I know the magnitude of the charge of an electron. It's that quantum little e. So that kind of notation I'm okay with right there for the magnitude of the magnetic force on one of these conduction electrons. Magnitude. Charge quantum little e. Now I would call that the drift speed and the magnitude of this external magnetic field. But now here's a question. What's the direction? I mean the direction of FB arrow, the magnetic force on this conduction electron. The answer, of course, is going to come from the right-hand rule, but what is it? I'd like you to think about that for just a minute. Pause the video, get an answer for the direction of that force, and then come back. Okay, so what is the direction of the magnetic force on this conduction electron? Well, we do it in 2 steps. First, we'll get the direction of this cross product or vector product, V cross B. That's straight from the right-hand rule. I like the 2-pen approach. I'll use the red pen for V and the green pen for B. And as I look down from above, The V is going upward in the plane of the screen, and the B is going into the screen. And so I use my right hand, palm out along V, so that I can push V onto B. My thumb, as I look at it, points to my left. So V cross B is that way. That's the direction of V cross B, to the left. But then I have to account for the effect of the Q in the force formula. It's a scalar, but it's a negative scalar for an electron, isn't it? And that means, because of that negative scalar, that the actual magnetic force is opposite to V cross B. So the F magnetic is that way. And what's the net effect of that? Well, this conduction electron is going to start to move along a curved path, being deflected towards its right because of that rightward magnetic force. Okay, does that seem reasonable? Let's go on then to the next slide, which now shows that curved trajectory, showing this conduction electron getting deflected over towards this right-hand side of this strip. Now that's happening to, there's a lot of conduction electrons. So what the net effect is we're getting a bunch of negative charge, excess electrons, building up all along what we'll call this right-hand side of the strip because of the magnetic force on these conduction electrons. Right? So we've got a buildup of excess negative charge on the right side of the strip. Excess negative charge on the right side of the strip. Then what we have on the left side of the strip, directly across, is what's called a dearth of electrons. We're lacking electrons. And that means we have left behind on the left side of the strip an excess of positive charge. Like so. Okay? So now we have an excess of positive charge on the left side of the strip. Oh, but now I've got a separation of charge, positive and negative. Guess what? That creates the electric field. Okay? So now we have an electric field E within the body of the conducting strip. It must not be a conductor in equilibrium, electrostatic equilibrium. It's not. Because that charge configuration like that is going to create an electric field, and it's going to be in the body of the conductor. And I know that electric fields point away from positive charge and towards negative charge. So I'm going to have an electric field all throughout this strip pointing from left to right, like that, all along the strip. Okay? That electric field is directed toward the right. That's from physics we already know. Okay? All right, now, and of course this has to be built up this way, this electric field. It's not there originally. That electric field is not there when we first turn on that conventional current. But the magnetic field is. It was already there. So this electric field will build up over time. It doesn't take very long. But it will build up over time. But the point is, we will have an electric field directed the way you see there with that arrow E. So now here comes the next physics point. Now we have the charge carriers also experiencing an electric force, F electric, Fe, and the formula is Q times E. So now here's a question for you. What is the direction of that force, F electric, on one of our conduction electrons? Right? You can see the picture there that shows our conduction electron and the F magnetic on it to the right. What's the direction of the electric force on this conduction electron? I'd like you to think about that, get an answer, and then come back. Okay, are you ready? So we're using this formula to learn about the electric force on one of our conduction electrons. We know which direction the electric field is in. E arrow is to the right within that conducting strip. But our particle is an electron. So the Q is negative little e. So what's the direction of Fe, F electric? Well, opposite to the electric field. So the electric force is that way. to the left, opposite to the magnetic force. You see that? Opposite in direction. F electric and F magnetic are in opposite directions. That actually makes sense physically. That means these two forces are competing with each other, F magnetic and F electric. And initially, all we have is the F magnetic, because there is no electric field initially. So all we've got is the F magnetic. But as that electric field builds up, as you get more and more charge separation on the two sides of the strip, electric field gets bigger, the F electric gets bigger, and eventually you're going to reach a kind of a special situation, a kind of stationary or a steady state, we will call it, situation, where the F electric and the F magnetic exactly balance. And once you get to that steady state configuration, then conduction electrons can just drift straight along the strip. Okay? And all of this happens relatively quickly. And that's really what we're interested in once we get to this kind of steady state. So now we're going to talk about that. It's a kind of equilibrium, this steady state, that will develop in which the two forces, F electric and F magnetic, balance because they have equal magnitudes in opposite directions, like the picture right here implies. So we're going to just denote that this way. Fe equals Fb, where when written like that, we mean the magnitudes are equal. Okay? And then, as I said, the charge carriers that haven't already been piled up on the two sides can pass along the strip undeflected. Remember, I have pretty much an unlimited supply of these conduction electrons. All right, so that's what we're interested in now, this equilibrium or steady state situation. So no more deflection. The V drift for the conduction electrons is straight up through the strip. And I've got an electric field within the body of the strip from left to right. And I've got excess positive charge on the left side of the strip and excess negative charge on the right side. But I know that associated with any electric field E, there's a potential difference. And this is an electrostatic field because we've reached steady state. Nothing's changing anymore. So there's a potential difference with this electric field. Okay? And I know that electric fields point from higher potential to lower. So that means I know the left side of this strip has a higher potential than the right side. So notice how we've written high and low. And if I put the leads of a voltmeter across the strip, left side to right side, with the common side on the right, and the common lead on the right, and the other lead on the left, the voltmeter would read a positive number, telling me that the left side had a higher potential than the right. And it's pretty easy to see what that potential difference will be between the two sides, the magnitude of it. Delta V is just the magnitude of the field times the distance that is labeled D in this picture. And it's very important to see that that's this particular distance in the strip from R left to right, if you like, the width of the strip. Okay, but to be a little bit more clear what that appropriate distance is, it's the distance that is perpendicular to both the drift velocity, Vd, and the magnetic field, B. Okay, so now let's put all these ideas together. We start with the balance equation for the force magnitudes. Fe equals Fb, magnitudes. Okay, for the electric force, magnitude of Q times electric field. For the magnetic force, magnitude of Q times Vd times B, all magnitudes. Okay? That's based on the picture you see right there on the left. The next thing I did is use an idea from chapter 26 on the right-hand side. I replaced the drift speed, Vd, with the magnitude of the current density, J, current density, in the copper, over N, the carrier density. That's what that symbol N is. The number of carriers, conduction electrons, per unit volume, and the magnitude of the carrier, charge, magnitude of Q. Of course, then I see that this, on the right-hand side, this factor of Q magnitude and that one cancel. And remember that current density magnitude, J, is current per unit cross-sectional area that the current is flowing through. So current per unit area, A. But we'll have to be very clear what that appropriate area is, and I'll talk about that in just a minute. Okay, so now I've placed J with I over A. That's that step. So I just consolidate everything and I get this result. Magnitude of Q, the charge carrier, the charge amount, magnitude of E equals just the plain old current flowing in the copper, I, times the magnitude of this magnetic field, over the carrier density for copper and the cross-sectional area of the copper strip. Then we substitute that E equals delta V potential difference over that width distance D, and we get this expression. Now I want to talk about what that cross-sectional area A is. Well, my top-down view here on the left doesn't help me see what that is. So now what I need is an end view. Okay, so again, if I imagine this book as being the strip, I can look down on it from above this way. The current's coming in this way and coming out that way. Or I can look at it end view this way, with the current coming straight at me. And then the strip looks like that. So I'm kind of imagining there's my eye right there, with the current coming straight at me. Then I see this end view I'm drawing over here on the right, where this diameter is what I've been calling, or this distance is what I've been calling the width, D. Okay, now the current is coming straight out towards us, right through here, I, the conventional current. And it's all throughout that area, right there. So that's the area A we're talking about. So I need one more dimension. I need to know one more thing. Just what's the thickness? The thickness of the strip this way. And we'll call that L. So the area A, the cross-sectional area through which the current is flowing, is L times D. Okay, all right, so with that in mind, we put in A equals L times D. Let me write down what that gives you. Let me just write it right here beneath where I was. Magnitude Q, potential difference delta V across the strip over D equals IB over NLD. Then the D cancels. And then what I did is just solved it for N, the carrier density. That's one possibility. Okay? When you do that, you get N equals IB over absolute value of Q, L, delta V. And what you've got is a way then, using the whole physics of what's going on here is called the Hall effect. And so we're using the Hall effect to measure the charge carrier density, little n. Assuming, of course, that we already know two things. Well, a number of things. The carrier charge magnitude, Q magnitude, the magnetic field strength magnitude, B, the potential difference, delta V, between these two sides here and here, okay, and L, the thickness of the strip going into the screen. And that's a way to measure the carrier density. Because you might have been wondering in chapter 26, where that concept of the carrier density first appeared, and we said, well, it's a property of the material. And for example, copper has a certain carrier density, a certain number of conduction electrons per unit volume, per meter cube. It would have been very legitimate for you to be thinking, well, how do you know what that carrier density is? You can't go in and count them. This is one way you can measure it. If you can set up this situation where you are able to know from measurements all the things there, then you can measure that, the carrier density. And then you know what the carrier density is for copper. Boom, you're done. You don't ever have to measure it again, if you don't want to. Okay? All right. Now, let's suppose you've already done this measurement for copper in order to figure out the N, the carrier density. And now you want to do more experiments with copper and the Hall effect. Okay? Probably the most common thing you would use it to do, I'm assuming you already know then the N and the Q, is you can use that formula up there to measure B, the magnetic field that the copper is in. You can use it to measure B. And that, in fact, is probably the most common use of the Hall effect in current times, modern times. Use it with a strip of conducting material for which you already know N and Q, and use it to measure B. Immerse the copper strip in some magnetic field and use this effect to measure the magnetic field. That is, in fact, what we're going to do in the next experiment in lab. We are going to use this Hall effect to measure B, magnetic field. Okay? Now, there may be a scenario, just to give you all possibilities, where you've got some conducting material. Maybe it's some compound that you've made with your chemist friend. And you know it's conducting, but you don't know what the sign or what the magnitude of the charge carrier size is, the Q. But from other measurements, you already know the N and the B and so forth. So you can use this formula to find Q. Okay? The point is, it's a very handy little formula there based on a very straightforward, relatively speaking, phenomenon in which if you can figure out somehow to know everything but one thing, then you can use this equation to get that final thing. And I want to show you one more thing you can get out of this. You can use the Hall effect to determine the sign of the charge carriers in the conductor. Remember I've said, and this is true in copper, that in most simple metals, the free charges, the charge carriers, are simply electrons, often called conduction electrons. But there can be situations, they're a little bit more complicated, and you would really need to take a class in solid-state physics before you would understand why, where the charge carriers are in essence positive charges. So therefore, with any given conductor, it's not safe to just assume that the charge carriers are negative charges like electrons. They could be positive. And so what if you don't know for a given conductor whether its charge carriers are positive or negative? The Hall effect can tell you which it is. Let me talk to you through how that will go. Well, look at the picture up above here on the left. That's the scenario for a strip of copper shaped the way you see, with conventional current I coming in at the top, going out at the bottom. And I know I can think of that as the direction of the conventional current. I would hook up a battery or a power supply with the high potential side there and the low potential side down there from the battery, the power supply, and therefore conventional current would go in this direction. And when I do that, I discover, because of the charge separation in the Hall effect, that the left side of the strip becomes the high potential side and the right side becomes the low potential side, and I can figure that out directly with a voltmeter and measuring the delta V. Now that's based on negative charge carriers. Now let's take the same shape conducting strip, same direction for conventional current, but now have positive charges moving. Okay, that's this picture right here. I've got conventional current I coming in at the top and out at the bottom, uniform magnetic field into the screen, but now my charge carriers are positive. And if they're positive, then their drift velocity, Vd, is in the same direction as the conventional current, because conventional current means motion of positive charges. Okay? All right, now let's briefly go through the steps of the Hall effect like we did before for the negative charge. First question, what's going to be the direction of the magnetic force on one of these charge carriers? That's going to be based on that formula. I'd like you to think about that. Get an answer, please, and then come back. All right, well, let's use the right-hand rule to get the direction of V cross B first. I like the two-pen approach, the red pen for V and the green pen for B, and I hold them with the V horizontal towards me and the B down. Okay, and I do the right-hand rule, pushing V on top of B, and I get the direction of V cross B is to my right. But then I have to account for the Q, that scalar out front. But this is positive charge, so that means the F magnetic is the same direction as the V cross B. So the F magnetic is to the right, which means that my charge carriers, which are positively charged, will get deflected to my right. And that means that I will, over time, end up with an excess of positive charge on the right side of this strip, and leaving me with an excess of negative charge on the left side. And that will create an electric field within the strip. The electric fields point away from positive and towards negative. So the E will be to my left. But then that means, because electric field points from high potential to low, that the right side of the strip is high potential and the left side is low potential. Note that that's just the opposite polarity of the potential difference to what I had with the negative charge carriers, right? See there, with negative charge carriers, the left side of the strip was high potential and the right side was low. If what you've really got is positive charge carriers for your conductor, then the right side will be high potential and the left side will be low. And you can easily determine that with a voltmeter. So this Hall effect can let you determine the sign of the charge carriers in a conductor. It is a very useful phenomenon. Okay? And as I said, we will use it in the next experiment. Okay, I'm going to leave you on this video with some practice. We're going to do it together. Okay? It's not going to be class engagement. We're going to do it together. But it's practice with the Hall effect. And it's a variation on what I was just talking to you about. Okay? We'll call it a phenomenon analogous to the Hall effect. And we're going to do it by moving a conductor at constant velocity v in a uniform magnetic field B, instead of setting up a current I. The way we'll get our charges to move, instead of setting up a current, is we'll just literally move the conductor in the magnetic field. Okay? Well, of course, the conductor contains charge carriers. They will then have the same velocity v as the conductor itself. They're coming along with it. Okay? And so we'll have moving charges in a magnetic field. So this figure shows a rectangular conducting block in a uniform magnetic field. You can see the magnetic field points to the right, which is the plus x direction in this diagram. And this rectangular conducting block has three dimensions. There's a length parallel to the x-axis this way, which happens to be the big dimension. They label that Lx. There's a length parallel to the z-axis. They label that Lz. And then there's a length parallel to the y-axis. They label that Ly. And it's pretty clear that Lx is larger than Lz is larger than Ly, just based on the shape of this rectangle. Okay, this rectangular three-dimensional object. And we're always going to move this block at a certain speed, v. They give us a number, 4 centimeters per second. Doesn't matter what the number is, just that it's always going to be that same v. And in different experiments, we're going to move this block first along the x direction, then along the y direction, and then along the z direction. And that's going to, in principle, create what's called a Hall potential across the block somehow. And I want to rank the size of that Hall potential according to whether I move the block along the x direction, the y direction, or the z direction. So for example, if I were to move this block along the x direction, see where the x-axis is? That means the v of the block is that way. Or if I were to move the block along the y direction, that means the v of the block as a whole is that way. Or if I move the block along the z direction, then the v of the block as a whole is along that way. Those are the things we're going to do. Those are the ways we're going to move the block. And we don't want to rank the size of the Hall potential or potential difference, delta V, set up across the block. All right, so this needs to be thought about a bit carefully. But one of the key ideas here is we're interested in what we reach when we reach that kind of equilibrium situation that we were talking about earlier, where on our charge carriers, let's just assume they're electrons. For this practice, that will be fine. So the magnitude of the electric force on a conduction electron will equal the magnitude of the magnetic force. And that will mean magnitude of Q, let's just call that little e, that's the magnitude of the Q of an electron, times the magnitude of the electric field that's been created inside the conductor because of this motion, will equal, again, the magnitude of Q, times the V that I'm moving this block at, magnitude, because that's how fast the conduction electrons are moving, times the magnitude of B. Now I should point out something, though. There's a little bit of a subtlety here. We worked out this kind of expression up above, assuming that the velocity vector for the moving conduction electrons is perpendicular to the magnetic field vector. Just keep that in mind. All right, then if this is what is happening and we reached equilibrium, we'll have an electric field created within the body of the conductor. That will have associated with it a potential difference. That will be delta V, and E will equal delta V over some appropriate distance here. I call it D, but we're going to have to be clear about what that distance is for our conductor we've got here. We called it D in the earlier pictures because we were literally showing you what that D was in the diagram. We're going to figure out what that appropriate D is for this conductor. And then over here on the other side, of course, I have little e, v, b. I see that the factors of little e cancel. I then just rearrange this for the Hall potential difference, that's the delta V. And we'll just write that as V magnitude, B magnitude, times what the appropriate distance is. Now here's an important thing to remember. This combination, the magnitude of V and the magnitude of B, that's going to be the same in all three cases that we're going to look at. Okay? Because we're always going to move it at the block at the same V, and it's always in this same magnetic field. So what the key thing here that is going to determine the potential difference, called the Hall potential difference or the Hall voltage, across the conductor is the appropriate distance that is involved. Okay? And that distance, d, well, that is the width of the conductor along the dimension that is perpendicular to V and perpendicular to B. And I need to figure out what that distance is, as I have been saying. And I'm going to do that now for each of the three cases they talk about. Let me remind you of what case number 1 is. I'm going to write that down like this. The velocity that I'm going to move the block at, the direction of that velocity, is along the x direction. Plus x. Okay, I'll even draw it up here. That way. That's the way I'm moving. That's the way I'm going to move the conducting block, which means that's the way the conduction electrons are moving. Well, this one is sneaky, this choice. All right? Anybody, you want to think about that for just a minute? Why is this particular choice for the velocity direction a little bit sneaky? But it's good physics. It's because the velocity direction is parallel to the magnetic field direction. V is parallel to B. See it in my drawing up there? V is parallel to B, same direction. But that whole formula for magnetic force includes V cross B, cross product. But the V and the B are in the same direction, they're parallel. So what do you get in a cross product when the two vectors are in the same direction? Did you say 0? There is no magnetic force. There's nothing here. Which means the conduction electrons aren't even deflecting. So you don't even get the buildup of positive and negative charge, which is what causes the electric field, which is what causes the electric force. You don't get any of this happening. There's no Hall effect at all. So there's no Hall potential. Delta V is 0. Done. Okay? A little bit sneaky, but good physics because you want to know that. Oh, I don't want to move the conductor that way. I'm not going to get any Hall effect at all. Okay, case 2. The velocity vector is along the plus y direction. Let me try to draw this block over here to the side. And let me try, just trying to show you the three-dimensionality of it. And let me draw over here to the side one of the conduction electrons. I'm drawing it to the side, but I'm assuming it's inside the block. And let's draw some vectors. Okay, now the y direction is up in this case. So the velocity is up for this case. That's the direction of V. Remember the magnetic field direction, B, is to plus x, which is to the right. Okay, those aren't parallel, so there will be a V cross B. So let's figure out the direction of the magnetic force on one of these conduction electrons. Okay? First do V cross B. Which way is that direction? If there's the V and the B. Did you say, for right-hand rule, V cross B would be into the screen? So what's the direction of F magnetic? It's an electron out of the screen. So I'm going to denote that. I'll use this picture, that way. That means that conduction electrons are going to build up on this rectangular surface here and kind of in the front. You see that? We're going to get negative charge building up on this face, all along it, on the front face. And that will leave a dearth of negative charge on the back face, so that will be positive. But then that helps me see what's the appropriate D, the appropriate dimension. It's got to be basically the distance from the positively charged face to the negatively charged face. That's this dimension right along this way. I'm trying to highlight it very clearly. That's the D I need to use to find the Hall potential. And then I would use a voltmeter across between those two faces like that. Now that D is, if you look very carefully at the picture up above there, that D is the distance LZ, right here. So the Hall potential created here, delta V, will be magnitude little v, B, and then the appropriate distance will be LZ. Now I'm going to let you practice the third one on your own, but what's happening in the third case is that the velocity vector is along the plus z direction. So I recommend you draw a picture like I just did for case 2, but you do it for case 3. And draw the velocity along z and the magnetic field along x, and figure out the direction of F magnetic. And that will tell you what face of the block ends up with an excess of negative charge, and what face of the block ends up with an excess of positive charge. And then you know what distance to use, because it's the distance between those two faces. And what you should end up being able to convince yourself that the formula for calculating the Hall voltage is little v times B, and the appropriate distance is Ly, which is this short distance right here. And then you can rank the delta V's. The biggest one is this one, because it involves the biggest distance of the three. Then the next one is this one, and then the smallest one is that one. So practice with the Hall effect is really helpful. We're not going to talk about it in class, so watching this video is important, but we are going to use this phenomenon to measure magnetic field in our next experiment. And that's all for this video.